In this video, we're going to finish deriving the integral relations for control volume analysis. Start by looking at a summary of the equations as we have them so far. We're looking at the conservation of mass equation, the conservation of linear momentum equation, the conservation of angular momentum equation, and the conservation of energy equation. So far, we have derived these equations as a time derivative of some system quantity which is derived from the system mass that we're tracking or following in a Lagrangian frame of reference. Mass conservation, the time rate of change of the system mass is 0. Linear conservation of linear momentum, the time rate of change of the momentum that that mass system has is equal to the sum of the forces acting on that mass. Conservation of angular momentum is just the moments of that, and conservation of energy, the time rate of change of the energy that that mass system has, is equal to the heat transferred into the system minus the work done by the system. We also saw how we could write the volume averaged form of that system quantity, which is shown on the right-hand side here. And so we can write the volume averaged version as a volume integral over the control volume that we're going to analyze. And that's shown for each case here. All of this is done in the Lagrangian frame of reference. We also derived the Reynolds transport equation, which showed us how if we have the time rate of change of a system variable that we're tracking, that fixed mass system, how we can transfer that into a Eulerian frame of reference or a control volume frame of reference with this Reynolds transport equation, whereby we have the time rate of change of a volume integral of some quantity plus the amount of that quantity that went out the surfaces of my control volumes minus the amount of that quantity that came into our control volume. So all we need to do now is apply this to these governing equations. So here we are with the Reynolds transport equation up top, and notice that that n system that appears in the Reynolds transport equation is summarized here for each of these equations. For conservation of mass, that n system is mass. For momentum, it's mass times the velocity. For angular momentum, it's r across v times the mass. And for energy, it's the capital E for the energy. And that system that is the beta in the Reynolds transport equation takes a value of 1 for the conservation of mass equation. You see then that integral over the volume, with beta being equal to 1, when I integrate the density over the volume, I'll get the mass. Likewise with beta equal to 1, when I integrate the density times the velocity normal to the surface times the area, I'll get the mass flow rate. It will be positive for outflows and negative for inflows. Similarly, if I set beta equal to the velocity, then this will integrate to the momentum in the volume, and this will integrate into the momentum which is transferred out of the system being positive, while the momentum being transferred into the area being negative. Likewise, if I set beta equal to r across v, then I will recover the rate of change of angular momentum inside the volume, and I'll be looking at the fluxes of angular momentum in and out of that system. And finally, for energy, if I put beta equal to the energy over the volume, then I will likewise record the energy. I will recover the energy in the volume when I carry out this integral, and the energy that is carried through the surfaces in and out by the mass flows that are going through there. And so when we apply that, we get the term that will replace that time derivative following the mass, so that we can apply it in the Eulerian frame of reference. And it's shown here for each of the 4 equations, simply substituting in the values that were on the previous slide. And so when we now put it together, and we see that of course that term that we had on the previous slide is equal to 0 for the conservation of mass. That term that we had on the previous slide with the momentum in it is equal to the sum of the forces, and I've broken them out here into 2 different types of forces. Surface forces, which act on the surface of my control volume, say pressure acting on that surface, or perhaps we could have a body force, say the mass of the fluid inside the volume. We may often neglect this term, but for completeness we can have those 2 types of forces, one acting on the surface, one acting through the whole body of the volume. And conservation of angular momentum, similarly, we can have moments of those surface forces, we can have moments of those body forces, and we could have any applied torques, or applied moments on the system. And so there's our full set of governing equations in its full integral form. And now let's look at some simplified forms of that, which in most cases we'll end up using. If it's steady, if our system is steady, what does steady mean? Steady means that the time derivative is 0. And so all of those volume integrals that we had, which had a time derivative in front of them, all go to 0. And so these equations simplify quite dramatically with that time term going away. Now we're left with simply the mass fluxes in, out, minus in of my volume are equal to 0. Or the forces, the applied forces, are equal to the difference between the amount of momentum that is carried out of the system by the mass flows minus that which is carried into the system by the mass flows. And similarly for conservation of angular momentum. And it's important to note, of course, that the conservation of momentum equation is a vector equation, and so we could look at this in two components. We could look at the x component of the surface forces and the x component of the body forces, and then we will change the velocity that we had there to the u component of the velocity, or the x component of the velocity. And this will remain unchanged because this term here is the one that when we integrate it over the surface gives us the mass flow that is carrying that x momentum in and out of the control volume. And similarly for v, for the y component, we have the y component of these forces, and we replace this term with the v, and the mass flows are carrying the v component of the momentum in and out of the system. We can make another large simplification. If the values of the velocities and the forces are constant at all of those places where mass is crossing the control surface, then we can simplify this much further. That integral of those mass flows going out and in will simply collapse to the mass flows out minus the mass flows in is equal to 0. And of course we can expand that simply to say that that's the density times the area times the velocity at all of the outlets minus the density times the area times the velocity at all of the inlets is equal to 0. For the conservation of linear momentum then, we'll still have our surface and body forces, and we have, if it's a constant, that integral will evaluate to the mass flow times the value of the velocity at the outlet. It will be positive for an outflow. The mass flow will be positive for an outflow, whereas for an inflow, the mass flow when we integrate it over the surface will be negative, and so we'll get the mass flow out times the velocity out minus the mass flow in times the velocity in. And when we actually use this, we'll have to use the correct sign for V out and V in order to see how these signs will work out in an actual problem, which you'll see in some of the examples in the course. And very similarly, again, for conservation of angular momentum, we will get the rho v dot n dA term integrating to the mass flows, which will be positive for an outlet and negative for an inlet. And therefore we'll have minus the m flows in and their mass flows in, and they're multiplied by the r cross v term, which we can write as rv sine theta, as we'll see in the example on the example for the moment and momentum equation. And of course we can write this also in component form. If we have a two-dimensional problem, then we can look at the x components of the forces being equal to the mass flows times the u velocity component, and the y components of the forces being equal to the mass flows times the v component. And I've just written the conservation of angular momentum equation here in terms of r cross v, and then evaluating that a step further to say rv sine theta, or the magnitude of r times the magnitude of v times the sine of the angle between them, where the mass flows out will be positive and the mass flows in will be negative, and this term will get its correct sign from the cross product of r and v in each of those cases.